So let's get started. So it's a pleasure to have Niel Brandt visiting us. So Niel did his PhD here at the IoA, graduating in 1996, working with Andy. And then he went to Harvard after that. And from Harvard, he went to Penn State, where he's been since then and is a professor. So Niel works on a variety of topics related to active galaxies, starbursts, X-ray binaries, and also on large X-ray surveys. This week we've been having a meeting on LSST, and one of the things that Niel does is lead the LSST AGN Science Collaboration. So he's been here visiting us in his capacity as LSST AGN Science Collaboration lead. And he's worked a lot on large X-ray surveys, and he's going to tell us about one of the largest X-ray surveys, data from the Chandra deep field set.
Great, thank you. Thank you for having me. It's good to see some old friends in the audience and be back at the place where I originally learned to do X-ray astronomy. So today, as heard, I'm going to be telling you about a good, hard look at cosmic supermassive black hole growth. We've been very fortunate over here the past 2 decades to have several wonderful X-ray observatories, Chandra, XMM-Newton, the New Star Observatory, and others. Today I'm going to tell you mainly about results coming from the Chandra X-ray Observatory, but I also will bring in results from XMM-Newton and New Star whenever possible as well, because they're both also fantastic observatories. I want to stress that I'm representing a broader team of people in this work. In particular, I want to thank many of my students who have worked on the Chandra deep field. Some of them are here. Due to the heroic effort of many of these people, this work has been possible. I also want to thank many of my postdoctoral fellows in the past, and many of these people, both the students and the postdocs, have gone off to have great careers in various areas. Dave Alexander, many of you probably bumped into him. He's head of astronomy at Durham now. Franz Bauer, I believe, came through as a postdoctoral researcher, and again, it's been a great pleasure to work with all these people. I also want to thank many collaborators worldwide. Certainly at Penn State, I've been very fortunate to work on data from the Advanced CCD Imaging Spectrometer, known as ACIS. This is going to be the instrument that has gathered most of the data I'll be describing today. The PI for ACIS is Professor Gordon Garmeyer. He's now Professor Emeritus. He was at Penn State for many years. And he developed and envisioned and developed this wonderful instrument, which sits back here at the focal plane of the Chandra X-ray Observatory. It is a imaging spectrometer, true to its name. So every photon that comes down has its position measured, but also its energy measured and its time of arrival measured. So we're doing true imaging spectroscopy with timing all in one shot. That's a wonderful thing about using CCDs to study X-ray sources. And I also, of course, want to thank my broader collaborators worldwide. These are the catalog papers of the surveys that we've led. I'll tell you about some of the details of this work in a little bit. And we've had, again, a lot of help from people worldwide, including several people from here in the UK. So here's the outline for the talk today. I'll begin by just motivating the general utility of AGN X-ray surveys. Why do them at all? Why are X-rays a powerful way to do this kind of work? And then I'll tell you about the Chandra deep fields in some detail. I'll go through some selected science results from the deepest X-ray survey to date, the 7 million second observation in the Chandra deep field South region. And then I'll end by telling you about some future prospects for the field. So let's start with the utility of AGN X-ray surveys. Well, to begin with, we've known for a long time that X-ray emission is nearly universal from luminous active galactic nuclei. You take active galactic nuclei selected in the optical or the radio or the ultraviolet or whichever you like, are almost always strong X-ray emitters. And the X-ray emission is thought to be made in this coronal structure in the immediate vicinity of the supermassive black hole. No doubt you've heard about this type of an idea from Andy in past talks. This corona is kind of like the solar corona, but it's far more extreme, having a temperature of order of 1 billion Kelvin. And photons from the accretion disk can be Compton upscattered in this corona. Say an ultraviolet photon can be Compton upscattered to form an X-ray, and that's producing much of the X-ray emission we see. Furthermore, sometimes X-rays that are produced in the corona can shine back down upon the disk, and lead to additional interesting spectral features being formed. Now, of course, this whole system here is a highly dynamic one, and this is a little animation we recently put together showing that dynamic aspect of the corona. This leads to, well, a lot of interesting phenomena. Most notably, it leads to strong X-ray variability from these systems. We often see these things varying by factors of several on time scales of a day or shorter, let alone how long they might vary on years or millennia. And so, in fact, that's an important thing to consider when interpreting results from these X-ray surveys. And I'll have some things to say about that later on in the talk. And then I also just want to show you the typical X-ray spectra that we see from these active galaxies. This broadband power law emission is thought to be the emission from that Compton upscattering process I described. At low energies, we often observe an excess above that, the so-called soft X-ray excess. And then we observe an iron K line and a Compton reflection hump. These are reflection features when X-rays shine back down upon that disk and interact with it. Now, the surveys that I'll be talking about from Chandra and XMM-Newton, the deep surveys typically detect sources most effectively in the band between about 0.3 and 8 keV. So sort of running from there up to about there. That's the relevant energy band we're working with. Recently, with the New Star Observatory, we're able to conduct deep surveys up to about 16 keV quite effectively. And I just want to stress that's a very broad bandpass. If you compare that to the optical bandpass, this grab on the electromagnetic spectrum we have is like a factor of 20 times broader than the whole optical bandpass. And so there's a tremendous diversity of phenomena that one can probe with that very broad stretch of the electromagnetic spectrum. Now, this X-ray source that I've just told you about, close to the black hole, of course, is embedded down in a galaxy. And the AGN light is usually substantially obscured both by nuclear material in the immediate vicinity of the AGN, as well as broader galaxy-scale material in many cases. And so the point is that in the X-ray band, X-ray emission being highly penetrating has a reduced susceptibility to absorption bias. And that's what's being shown with this little animation here. Here what I'm doing is I'm taking that same spectrum I just showed you in the previous slide, and I'm adding absorption to it. The column density of absorption is labeled there, okay? And to give you a sort of a sense of things, the column density through your hand is of order 10 to the 23. The column density through your chest is of order 10 to the 24. And so the point here is that with X-ray emission, you can, especially with higher energy X-rays, penetrate through large amounts of obscuring material and find AGNs that would otherwise be difficult to find. And of course, another great thing about X-rays, in contrast to say the optical UV, is that absorption bias actually drops as you go to high redshift. As you go to high redshift, this whole thing cosmologically redshifts down, you gain access to increasingly penetrating rest frame X-rays, and so your absorption bias actually gets less and less as you go to high redshift, and this actually is very powerful for high redshift studies. I'll say some about that later on as well. And then finally, another great aspect of doing these X-ray surveys is that X-ray emission has low dilution by host galaxy starlight. Here's a well-known active galaxy. This is one of my favorites to study in the local universe, and this is an optical image, and this is its corresponding X-ray image. And I haven't done any trickery with the scaling or anything. The point is that essentially all the starlight drops out, and you just see the nuclear black hole light to a great extent in the X-ray band. And this is extremely important out at high redshift, because out at high redshift, you don't have the luxury of being able to go in and spatially resolve the AGN light from the whole starlight. So you really need a method of finding these things that maximizes the contrast between black hole light and starlight to get the cleanest possible samples of these AGNs. Now, of course, X-ray emission by itself is not perfect. I think it's nearly perfect, but not perfect. And so, best of all, of course, is to combine the X-ray surveys with all the wonderful multi-wavelength surveys that are available. And I'll say more about that soon as well. Okay, so a few words about these X-ray surveys. So all those positive aspects of X-ray surveys, the universality of X-ray emission, its penetrating character, its large contrast between black hole light and starlight, have led to a lot of X-ray surveys being performed. And here's a little plot that sort of summarizes the X-ray surveys in terms of their flux limit versus their solid angle. And you can see there's many surveys here. I'm just going to show you a couple of examples of these surveys if you're not familiar with them. Let's start here with the XXL survey. This is a very large investment here of time made with the XMM-Newton Observatory. This is the XXL-South field, and for comparison, that's the size of the full moon there on the sky, okay? So this is a 25 square degree survey done with XMM-Newton. It detects a large number of point sources, about 10,000 point sources, and, you know, being a very large area survey, it's powerful at detecting the rare luminous sources that you wouldn't find in narrower field surveys necessarily, but because of its rather shallow depth, it actually misses about most of the cosmic accretion power. Here's another example. Here's the Cosmos survey, which is another extremely successful project. Here's the Cosmos survey there. I'm focusing, in fact, on the Chandra version of it shown there. The Cosmos survey is a 2 square degree survey, and it was very well designed, I believe, to have a good combination of getting a large enough solid angle to get lots of sources and to see cosmic structure, but also getting sufficiently deep that you get a good fraction of cosmic accretion power in the survey. And they get about 4,000 point sources in this survey. And anyway, that's another nice example of a survey. But my favorite surveys, personally, are the Chandra deep fields. And so I'm going to now tell you about the Chandra deep fields in some detail. So the Chandra deep fields are the ultimate in pencil beam surveys. Chandra has allowed enormous advances, making extremely sensitive surveys. I mean, I remember when I was a graduate student here, I remember hearing about this man, Günter Hasinger in Germany, who had gotten a survey down to 2 times 10 to the minus 15. And I thought, wow, that's amazing. He went so faint. And what new sources is he finding? And, you know, Chandra has allowed us to go now, you know, a factor of like 100 times fainter than that, or even somewhat more. And so it really has been wonderfully powerful at getting very deep observations. And here are the Chandra deep fields. There are 2. The Chandra Deep Field North is shown here. It's located near the Big Dipper on the sky. This is the Chandra Deep Field South in the constellation of Fornax. This is a 2 million second observation with Chandra, and that's a 7 million second observation now with Chandra. These have been gathered over extended periods of time, which lets us study variability of the X-ray sources over time, and they cover good solid angles. Each one covers about 60% the size of the full moon on the sky. And in these surveys, we get large numbers of sources. Here we have about 755 sources, the majority of which are AGNs. And also in this one, we have about 1,055 point sources, again, the majority of them being these active galactic nuclei. And of course, remember, for all of these little point sources we're seeing here, we're not just getting an image. We have spectral information and variability information for all these sources, so we can go and slice and dice our data this way. And now I'll just show you the very central part here of the Chandra Deep Field South. That's the central part of the Chandra Deep Field South. This is from a recent catalog paper by my former student, really an excellent student, Bin Luo, who's now a professor in Nanjing. And this shows the large source density in the central part of the Chandra Deep Field South. And just to sort of give you an idea of Chandra's wonderful sensitivity, the faintest sources we detect down here, we're getting about 1 count coming in every 10 days. Okay, so that sort of shows you that Chandra really is a remarkably well-designed instrument to be able to go down to those kinds of fluxes. We also have a lot of excellent other X-ray coverage in the Chandra Deep Field South. In particular, NuSTAR has spent a lot of time observing the Chandra Deep Field South. This is the NuSTAR image of the Chandra Deep Field South running from 8 to 24 keV. This is by Mullany, who many of you know here in the UK. And NuSTAR is very powerful, again, for giving us access to the higher energy X-rays. But because it has a rather large point spread function, its sensitivity is somewhat limited. And so in this sky region, they get about 19 sources, where we're getting about 1,000. But NuSTAR, again, is nevertheless extremely important for letting us ensure that we're not missing any substantial numbers of very highly obscured AGNs. I'll also point out there's also 3 million seconds of Chandra Deep Field South coverage with XMM-Newton, and that's very powerful for doing spectroscopic studies of the brighter X-ray sources. So now I want to address this question that I'm often asked and sometimes prodded about, and that is, why did you go so deep? I mean, why did you spend all this Chandra time doing these surveys? And there are 2 big reasons for it. One of them is to detect new sources. And by that, well, I mean obscured, growing supermassive black holes running all the way through the era of massive galaxy assembly from redshifts of 1 to 4. I want to be able to find all of these systems, be sure I found them all, and this is the way to go about it. Furthermore, we can also learn things about growing supermassive black holes in the first galaxies, and I'll say some things about that later on. And then finally, we're also able to study X-ray binary populations in cosmologically distant normal and starburst galaxies. So those are the sources we've gone after in these very deep surveys. And then I would say equally important to just finding new sources is just understanding the sources that we detected even with a millisecond exposure much better. We are always struggling in these surveys to get enough photons to really characterize the sources well. Chandra, and going very long with Chandra lets us do that. We get sufficient photons to characterize AGNs producing most of cosmic accretion power via their X-ray spectra and via their variability in the Chandra Deep Field South over a 16-year period. And Chandra, despite the fact it has a smaller collecting area for photons than XMM-Newton, is extremely powerful in this regime because its excellent point spread function gives us very high signal to noise, so we can cleanly characterize the spectral variability properties, even of quite faint X-ray sources, very well. And I'll just show you a few examples of such studies. Here's one led by my current student, Guang Yang, where we used the X-ray time-resolved data to study X-ray variability over 16 years in the 7 megasecond Chandra Deep Field South. And you can see sources coming in and out there. And so we've been able to characterize over, well, now almost 2 decades, the X-ray variability properties of typical AGN reaching out into the distant universe. And here are some examples of our spectral variability studies. This is a case where you can see nice variations in the flux level or the luminosity being generated by this system, whereas in this system we see spectral changes likely associated with changes in X-ray absorption. And we can do this, again, for large numbers of sources and characterize how this variability occurs. And then furthermore, with the excellent spectra, we can also go and just characterize the typical absorption levels of these active galaxies. This is a plot showing the distribution of column densities for these systems. And the typical source has a column density of order 10 to the 23, okay, inverse centimeter squared. So again, the typical AGN in the universe has an absorption column on it comparable to that for your hand. That's a useful thing to remember. And we can also characterize that absorption as a function of luminosity and redshift. And we find, for example, that the amount of absorption generally drops as you go to higher luminosities, and it also generally increases as you move to higher redshifts. So getting spectral lets just do things like that.
So how do you know there aren't more beyond 10 to the 24?
Yeah, well, okay, we have a number of, I suspect there are many. Okay, how do we know it? A couple of approaches. One, well, New Star helps a lot with that by pushing to higher energies. That's one way that we do it. You can also use multi-wavelength data. If you have a source absorbed by, say, 10 to the 26 or something like that, a lot of energy will be, the X-rays and the ultraviolet will be absorbed in that material. That has to come out as waste heat. So we can combine the X-rays with the infrared, for example, to learn how many such systems there could be. And there are some. They contributed about the 30% level according to our current estimates, but they're not leading to a catastrophic underestimate. That's the idea there. Yeah. Okay. So right. So that's going back to this. That's one of the issues about just understanding the current sources. And just to elaborate on it a little bit further, for spectral characterization, by doing these very long observations, we can do good spectral characterization reaching sort of 20 to 3 times below the Niel luminosity function from low redshifts out to high redshifts. And I have a plot to show that here. This is a plot just showing the Chandra Deep Field South sources, their luminosity versus redshift. This is the Niel, the luminosity function, I believe, coming from some work that, in fact, James here did, sort of measuring the Niel, the luminosity function. And we can, again, measure sources going well below the Niel, the luminosity function, where a lot of cosmic power is being generated. And I'll also just show you another example. Here's the Cosmos survey, which I showed you earlier. They can only characterize the sources above the Niel, the luminosity function. Now, we can of course, detect sources well going below it, but characterization is extremely important if you want to work out the nature of these sources. Best of all, of course, and I'll tell you about that later on, is to combine the strengths of surveys like this with surveys like that to get the full population, and that's in fact what we do. Now, I want to say a few words about the wonderful multi-wavelength data we have in these fields as well. This is absolutely essential to getting the best science out. This, of course, is the famous Hubble Ultra Deep Field. This sits right down in the middle of the Chandra Deep Field South there. And there also has been substantial, and I really mean substantial, additional investments of Hubble Space Telescope time on these fields. This is the famous GOOD survey, and some of you have probably heard of the CANDLE survey. They're also conducted in that region. So we can take the X-ray sources and match them up to Hubble sources to learn about the morphologies. And I'll show you some things about that in a minute. Just as this is quite interesting, I heard this recently from Garth Illingworth. He estimates that there's about 6 million seconds of Hubble time now that's been invested in the Deep Field South region. That's about 70% of a Hubble cycle, and if you price that out, it's about $250 million of Hubble time. So it really is worth pushing on this field hard to make sure we get our money's worth. Okay, so we have a lot of additional amazing data as well. There's been extensive spectroscopic campaigns on these fields, extensive imaging campaigns from many ground-based telescopes. Spitzer and Herschel have conducted some of their deepest surveys in these fields. ALMA is now doing a great job studying all the sources in this field. This is, again, led by many of the Durham folks. And the VLA has conducted extremely sensitive surveys. And all these multi-wavelength observations are critically important for just identifying the X-ray sources, figuring out what they are, and then classifying them, determining their basic nature, and also measuring things like their host galaxy properties. And this has been equally important as just pushing the X-ray data deeper in terms of keeping the science exciting. People sometimes ask me, well, aren't you bored after 17 years of doing this? And the answer is actually no, I'm not. I'm actually more energized than ever. And it's partly because the X-ray data get better, and equally because all this multi-wavelength data gets better, which lets us understand the X-ray sources better. Okay, so here is our current breakdown in terms of source number counts. Shows the number of sources per square degree we measure going down in X-ray flux. And the dominant population over almost all the flux range that we've measured are the active galactic nuclei. Here they are in the blue. And at the very faintest levels we're reaching about 24,000 sources per square degree in the central part of the Deep Field South. And if you scale that up to the entire sky, that's about 1 billion active galaxies across the entire sky. We're doing very well if you compare us to other methods of finding AGNs. We beat the deepest optical survey by about a factor of 20. And when we compare the X-ray selection to other wavelength methods of selection, infrared, for example, we do very well, particularly considering purity. That is, when we say something is an AGN, we don't just sort of mean it at the 50% level. We mean it at sort of the 100% level. And that's extremely important. And we're resolving sort of 80 to 90% of the X-ray background up to the 6 to 8 keV. Now, I'll also just mention that in addition to detecting large numbers of active galaxies, we do have this additional population of just normal and starburst galaxies we're detecting out to cosmological distances. And these, what we're detecting, are X-ray binary systems, the collective emission from all the X-ray binary systems in these objects. And here, as you push down to the very faintest soft band fluxes, we are finally getting to a regime where we're actually detecting more normal and starburst galaxies in the X-rays than we are even AGNs. And so this has been a very exciting thing to study. I won't talk about it much today, but I've actually had 2 students who have done excellent work for their PhDs investigating these and learning about the cosmological evolution of X-ray binaries in the universe. Okay, so how are we doing on sort of identifying all these sources? Well, that multi-wavelength data really has been wonderfully powerful in this regard. For our most recent 7 megasecond catalog, we worked very hard on getting reliable counterparts, which involved a tremendous amount of work locking down our positions. We actually improved them even more than you would have expected just from the photon statistics. And we have now 98.4% of the sources having counterparts. And for those, we have 97.8% of them having redshifts. Okay, and in fact, I will argue that the remaining 2%, many of those are probably actually false X-ray detections. And if you look at those redshifts, about the majority of them are now spectroscopic due to the enormous spectroscopic investments made in these fields. And about 33% of them are photometric. The photometric redshifts are very good. Here's an example. I mean, clearly deriving photometric redshifts for AGNs is a very challenging endeavor, but we have managed to do very well. We typically have sort of 20 to 40 photometric bands we're using in the photometric redshift fitting, and you can see we get sort of redshifts typically good to within a few percent. This is again, the spectroscopic redshift distributions here for the AGNs. They reach out to redshifts of about 4, as well as for the galaxy, we reach out to redshifts of about 1. And here they are fine-binned, and you can see we're picking up spikes of large-scale structure in the distribution. So here are some examples of HST imaging of the sources. Here are examples, for example, of the AGNs. All the ones labeled AGNs here are the ones we think the accreting supermassive black hole is dominating the X-ray power. They span a wide range of redshifts. The redshifts are here in each panel, and we have many very bright, we have many quite bright AGNs, many that are very faint, and again, we have lots and lots of these sources to sort of characterize statistically to learn about the populations. Here's another page full of them. So again, these are a lot of fun to look at. I sometimes spend hours looking at these things. Here's another page, and we have page after page after page of these things. So anyway, it's very useful to do this powerful way of statistically characterizing with truly excellent data, the nature of where most black hole growth in the universe happens. So now what I'd like to do is tell you about some selected science results from that very deep X-ray survey. And I want to stress that I'm not going to go through every little detail of these studies. I'm just going to give you an overview of some of the things we're finding. For many more details, I will refer you to a number of good reviews that you can find. One of them, Dave Alexander and I worked very hard on, and this will discuss many of the key details that I'm going to have to suppress here due to the limited time. So first I want to tell you about some work that we've been doing quite recently with my graduate student, Wang Yang, and it involves essentially trying to address this question: what matters for supermassive black hole growth? I mean, what is it about a galaxy that sets how much a supermassive black hole is going to grow? Well, there have been a number of ideas here. For example, a number of people, this is some work by Chen-Ting Chen, who's currently my postdoc, although this work he did at Dartmouth University, has argued that star formation may be an excellent predictor of black hole growth. To do this, what he did is he took sets of galaxies, binned them up by infrared luminosity, or equivalently by star formation rate, and measured their average X-ray luminosities by stacking them. And he adopted this approach, which is a very important approach to take because of that variability of AGNs that I mentioned. Again, the observations that we get right now of the Chandra deep field south, could be very different if we went and conducted that same experiment 1,000 years from now, or a million years from now. And so we want to average over the population of galaxies to try to get a statistical average of the amount of black hole growth occurring in the galaxy population. And when he does that, he finds this relation here, only over a limited range. I'll show you a better example of this in a minute, which appears to indicate there is a broad correlation between star formation rate and accretion rate in galaxies. So that's one idea. That's one of the leading candidates. Another leading candidate people have put forward is stellar mass. This is motivated by a number of arguments. One of them is just a simple one as shown here, and that is if you look at the fraction of galaxies hosting an active nucleus that has a luminosity above a given threshold, and here are the threshold numbers, that fraction rises strongly with stellar mass, as you can see there. So maybe mass has a big thing to do with it. The great challenge in sort of discriminating between these two leading candidates is this issue here. It's the so-called star formation main sequence, which is basically a rather simple thing. It basically just says that a galaxy of a larger stellar mass is generally able to support a larger star formation rate. This is a well-established relation. Not all galaxies follow it, but a large fraction of them do. Here's a little schematic put together by the Candles people showing the same idea here. So this is a great challenge because these two things are interrelated, which makes it very hard to disentangle which of these matters. Well, we set off to try to solve that, and we did that using, again, the ultra deep X-ray data. What we did is we went and we took a sample of 18,200 galaxies in just the Candles region of the deep field south. This is the region with the very highest quality multi-wavelength data. These galaxies have been extensively characterized, and good estimates exist, the best possible in any field in the sky, of their stellar masses and their star formation rates. And we then use the 7 megasecond X-ray data set to estimate the black hole accretion rate averaged over the galaxy population. So again, we're taking samples of galaxies where for all the ones that are individually detected, we are fitting their X-ray spectra to measure their true X-ray power generation rates. And for all the ones that aren't X-ray detected, we stack those galaxies up so to make sure we're not missing any power from them. We add it all up and we work out the total, and we scale that to reduce the black hole accretion rate. And that's what's shown here. And we work this out as a function of star formation rate at redshifts of 0.5 to 1.3 and 1.3 to 2. So these are two different redshift bins shown here. And focus on the black points for now. And you can see, just like what Chen had found back in 2013, there's this very nice relation. Now, one thing here is that we were able to push to much lower stellar mass and star formation rate than past work. And that's extremely important to obtain leverage for breaking possible degeneracies due to the star formation rate sequence. And in fact, we find that there are some significant degeneracy problems in these analyses. In particular, what we did is we took the galaxies that we had used in these stacked analyses, and we just split them by stellar mass. We split them at the median stellar mass, and we then performed the same analysis for each subset. And that's what's shown in these plots by the blue points and the red points, and they're labeled as there. And you can see obviously that if you split them at the median stellar mass, there's a very clear mass dependence. These things split apart by about a dex, okay, in stellar mass. And that is telling you pretty clearly that stellar mass cannot be the only factor driving the black hole growth. There has to be something else involved. And I will just say that people were hoping this would be the answer because it had an attractive idea behind it. The idea being that the amount of gas in a galaxy may largely set the star formation going on in that galaxy. And you can imagine that gas either going to forming stars or feeding the black hole. And if they're doing that at a roughly constant rate, you could imagine a relation like that being built up. However, we pretty clearly find that cannot just be the only answer. And in fact, we've pushed that even further now. That finding, that splitting upon stellar mass, led us to actually go and perform a partial correlation analysis, to try to break the degeneracy between star formation rate and stellar mass in determining black hole accretion rate. And that's in fact what's shown here. These are the results of the partial correlation analysis. What I'm showing here are the residuals from the observed black hole accretion rate compared to the best prediction here based on a stellar mass dependent model. And you look at the dependence of that upon star formation rate, there's only a rather weak dependence. Whereas if you look at the best star formation rate dependent model, there's a strong dependence upon stellar mass. That's a strong hint to us that in fact stellar mass is likely the primary driver here in setting the black hole accretion rate. And here are the quantitative results from our partial correlation analyses if that's of interest. And in fact, our best finding, given the rather weak residuals remaining from a pure mass-based model, and here in fact is our best mass-based model here, that's black hole accretion rate as a function of stellar mass. Again, you have a nice linear relation over the range of that we're fitting, at least, in these two different redshift bins, that in fact stellar mass could be the whole thing, as far as we can measure, at least right now. Now I will stress that this work applies for sort of typical moderate luminosity AGNs in the universe. It may not be entirely applicable up in the powerful quasar regime, and I may say more about that later on if I have a chance. So, since we have this hint that stellar mass is very important in black hole growth, we've considered this, pushed this further. We've looked, for example, at the rate at which the black hole is growing relative to the rate at which the galaxy is growing with stellar mass, and that's what's shown here. And what we find as a function of stellar mass, as you might expect, given the mass dependence of black hole growth, is that, well, black holes grow faster relative to the stars in the galaxy for higher mass galaxies. You can see that general trend rising up along there. In other words, more massive galaxies have higher black hole divided by host growth rate ratios. Now, why is that? Well, we're trying to understand that now. It could be due to deeper potential wells in more massive galaxies, promoting supermassive black hole accretion and counteracting feedback. Or it could just be that stellar mass is actually a tracer of a more deeper effect, some other aspect of the galaxy that actually decides the amount of black hole growth. Now, we've generalized this recently. We had some limitations in this form work. You can see we only had 2 redshift ranges. We had quite large error bars in a number of cases. We've recently substantially improved the work in the following way. So Yang et al. Suffered from limited coverage of high stellar mass systems. We were using these rather narrow fields. Furthermore, we have limited constraints on cosmic evolution. We only have those 2 redshift bins, and we were limited to rather low X-ray luminosities. We've recently gone and combined the deep field south, the deep field north, and cosmos together, taking a cue from what we just found in the deep field south to do this analysis much better. And as I already pointed out, the sources that we're detecting, combining the Chandra deep fields, labeled here as the goods fields, and cosmos, give us plenty of sources just in terms of detection to get almost all of cosmic accretion power, and also in terms of spectral characterization, as I said. And here are our current results, which are really substantially improved from that first paper. This is currently a submitted paper. And this shows our best derived relation between average black hole accretion rate, again, averaging over the galaxy population, versus stellar mass. And we're now, due to our much improved sample, able to reach out to high stellar masses as well as quite high redshifts. And we find that black hole accretion rate generally increases toward high stellar mass with a much stronger dependence at high redshift. Another sort of equivalent way of saying that is that the black hole accretion rate has a stronger redshift evolution at higher stellar masses. We're here at high stellar, you can see the very dramatic evolution there over many orders of magnitude. One thing that I find quite striking about this relation is that it keeps going all the way to redshift 4. And you might say, well, that can't be true, because we know the quasars go down beyond a redshift of about 3. So, how can this be? Well, what it indicates to me is that, remember, we're averaging over the galaxy population here, that essentially the decline of the quasar population beyond a redshift of 3 or so has to be driven almost purely by the number of available sites in which to grow the black hole. In other words, the black holes themselves don't have any problem with growth. You give them a site to grow, you will manufacture the black hole. It's just that the number of sites available are not sufficient. And I'll say more about evidence that indeed is likely the case in a minute. So we've also significantly improved this relation between black hole accretion rate and star formation rate that I showed you previously. Here is our current modeling of it, again, as a function of redshift. And what we find is that, well, at low redshift, interestingly, the black hole accretion rate stellar mass relation, okay, and the star formation rate, stellar mass relation, have rather similar shapes. And so the ratio of these two things is actually rather flat. Whereas at high redshift, the black hole accretion rate actually increases more strongly with stellar mass than the star formation rate does. And so clearly, from that result, you expect low mass galaxies to have undermassive supermassive black holes compared to the famous black hole stellar mass relation that has been established primarily for massive galaxies. And in fact, here's our prediction of that. And in fact, interestingly, I mean, once you have this relation combined with the stellar mass function of galaxies, if you believe that stellar mass is indeed the driver of black hole growth, essentially reduces black hole growth in the universe down to a matter of quadrature. Okay, you just do the integral and you know what it will be. Now, that relation may not be strictly true, but that's what it implies. And so we can actually calculate the predicted ratio between the mass of the black hole and the mass of the galaxy at any redshift, subject to initial conditions up at very high redshift. And what we predict down at redshift 0, essentially integrating up this relation over all of cosmic time, putting in the stellar mass function, which we get from work by Baruzzi et al., is that the ratio between black hole mass and stellar mass should run from about 1/500th up at very high stellar masses of galaxies down to about 1/5000th for low stellar masses, simply as a consequence of this differential growth. Okay? And so the point here is that, well, you can't necessarily expect this thing just to follow a simple power law relation that people have typically expected. Now, clearly the data, which are plotted here, are rather scattered. Obviously, as you can see, we actually expect that because of the growth of these sources at different cosmic times. We're actually trying to compute what the scatter should be right now, but what I can say is that, broadly speaking, our measurements actually seem better in agreement with this large population of objects down at rather low stellar masses that have rather undermassive black holes compared to what you would have expected from these linear or power law type relations. And furthermore, I'll just mention that this relation, this running from 1/500th down to 1/5000th, largely is frozen in at about a redshift of 2, as you can see from here, because essentially there's so little growth down at the lower redshifts that it really doesn't matter much. Okay, so now that was one topic I wanted to cover. I now want to say a few words about pushing toward very high redshift. Okay, so what have the Chandra deep fields taught us about black hole growth in the very early universe? And we've done a lot of work on this as well. This has been led by a very good postdoc currently in my group, Fabio Vito. A paper just came out yesterday on Archive, maybe some of you may have seen. One thing is we put in a lot of work using the best possible X-ray data, the best available photometric redshifts, doing proper statistical Monte Carlo treatment of uncertainties, and propagating everything through to get the best measurement of just the space density of active galaxies of different luminosity classes, as labeled here, as a function of redshift. We find up at high luminosities results that are very consistent with what people had found previously. Those there are the blue dots. And then as we move down to lower luminosity classes of AGN, the green dots, and then ultimately the red dots, and these open red dots are our preferred solution for technical reasons you can read about in the paper. We find that in fact, if anything, the decline at low to moderate X-ray luminosities out at high redshift is in fact, if anything, slightly steeper than that at high luminosities. And of course, this has a significant impact for missions like Athena, which aim to go search for a high redshift AGNs. If they're dropping off steeper than the high luminosity ones, that unfortunately will mean there are less of them out there to be found. Another point to make, which I want to highlight, which connects to what I just been saying, is that if you look at the decline of the high luminosity systems, the quasars, essentially, which are shown here as the blue points, you can see that their slope of decline actually matches rather well with the slope of decline of massive galaxies at those redshifts. So it actually locks together very nicely. Very consistent with what I was saying back here about the number of sites being the driver of evolution. Again, all the way to the end of the universe, you give it a site to grow, it will grow. It's just purely a site-driven effect that is causing the decline. You just don't have as many places to grow them. Okay. We've also done a lot of additional work to constrain, for example, the obscured fraction. Here's our current estimate of the obscured fraction of objects out at high redshifts. And again, I'll remind you that out here, we are actually sampling up to like 40 keV in the rest frame, very penetrating X-ray, so we have rather little absorption bias. And we find that about 60% of the sources are highly obscured, okay, even out at very high redshifts, down at the sort of moderate luminosity. Okay, so that's one thing that we've done. We've also been working hard to try to push the data as hard as we can to try to learn about the seeds of the first supermassive black holes. We'd like to know things like, do the black holes that ultimately go on to form the quasars form by a direct collapse? Do they form from sort of a few hundred solar mass stars that collapse down to form a few hundred solar mass black holes that then ultimately must grow via Eddington limited or hyper Eddington accretion? We'd like to be able to say something about that. Well, this is a very challenging thing. Even for Chandra, the sensitivities with even a 7 million second exposure is very challenging. But we use kind of a trick to do this, and it's one of my favorite tricks. It's stacking. And here's what I mean by stacking. This is a nice plot put together by one of my students, Brett Leamer. It's one of my favorite plots ever made by one of my graduate students. What he did is he took a bunch of T candles and he put them on his stairs, and he took an observation, a 3/100 second exposure. And there's the 3/100 second exposure. And then he took another exposure of those same T candles with a 1/1000 second exposure. There it is. And clearly there's a lot less information in there than there is in there. But then he went and he took these 30 heat candles with these short exposures and he stacked them all up, and that's what you get. You can see you recover the flame very nicely. You can see there the candles wax. You can even see the end of the wick there. And so this stacking really works. I call this the romantic example of stacking because he put this together around the time he got engaged to his girlfriend. It's a very romantic picture. Nevertheless, so we use this exact technique, stacking, to go and try to constrain the seeds of the first black holes with the Chandra deep fields. What we do is we essentially do exactly what we did with those candles. We performed X-ray stacking of individually undetected galaxies that have been found in the deep multi-wavelength surveys of these fields. And we have between about 100 and 1,400 objects per bin. And Fabio has written a very nice stacking code to do the analyses of this. And what we find is that you can pull up average detections out to regions of 4.5 to 5.5, as shown here. So these are basically images. The top set of images here show galaxies of all masses that we stack. The bottom set here shows just the most massive half of the galaxies. And in fact, we find that most of the X-ray signal comes from the most massive half of the galaxies. And these are, very impressive exposures. I mean, this here is a 265-year Chandra exposure. And so if Chandra observed the deep field south for 265 years, something that I would propose, but surely would not be accepted, then you could detect all these galaxies individually. Here's an 86-year exposure. There you can pull up the detection. Similarly there and there. At higher redshifts, we don't get detections, but we can get very tight upper limits on the amount of black hole growth that can be there. And we then go and decompose this signal, try to interpret what the X-ray signal here is from. And we find the signal appears to be mostly from high mass X-ray binaries in massive galaxies. That is, we know the stellar masses of these galaxies, we have estimates of their star formation rates. We can calculate from all the extensive work we've done at low redshift on X-ray binaries how much X-ray binary power should be from these galaxies. And most of the signal here, in fact, appears to be consistent with that from X-ray binaries. And so one immediate deduction is that out to the redshifts we've been able to probe so far, most high redshift supermassive black hole accretion, even out in the very early universe, is occurring in the short AGN phase. Any continuous low rate accretion contribution has to be small. And this plot here sort of summarizes that.
Good question.
Yeah, sure.
When you use the word redshift,
yes,
at the highest redshifts,
yes,
most of these are photometric redshifts.
many of them are photometric. That's right. We have pushed very hard to get spectroscopic redshifts for as many as possible, but these sources out of the very high redshift, not surprisingly, tend to be very faint. However, that being said, we have excellent photometric redshifts. Even out of these redshifts, you're just locking in mainly on the line and break. And that gives a very good job of locking the redshift. And remember, we have, for these objects, between 20 and 40 photometric bands we're using in the photometric redshift analyses. So they are very good photometric redshifts. And we, in the analysis, and I haven't gone through all the technical details, but you can read them in the paper, we actually carry along the full photometric redshift PDF, and we Monte Carlo that through the full analysis when we reach our final conclusions. Does that answer your question? Well,
I mean, sometimes you have to turn it around. Well, how many of the redshifts would need to be at lower red?
Yeah, how many? Right. Okay, so
because you're in unknown territory, right? That's the issue. That you can't.
That's what. Well, yeah.
Your prior, you're assuming a prior that may be wrong on the redshift.
Well, we're mainly just looking for the line of break. These are primarily set by the line of break.
There is degeneracies, right? It's just
sure, there are degeneracies.
It doesn't detect that.
Well, I can tell you. Okay, what I can tell you is this: we have certainly worried about things like, for the large low redshift population of active galaxies, due to catastrophic photo-Z failures, how many of those could be artificially scattered up here? We estimate that could happen. You can look in the paper. I believe it's about 6% of our sample could be due to that type of an effect. That's not enough to qualitatively change any of our results, because again, we Monte Carlo that through the full analysis. And for all the gory details, check out the paper, which appeared on arXiv yesterday, one of them. Okay, so here are the current results, showing both our results from direct X-ray detection, shown here, as well as from stacking, shown here. Okay, and we're showing results from the stacking, both again for all galaxies, as the open circles, as well as just the most massive half of galaxies, shown as the squares there. And so the point by doing this, both the combination of direct detection and stacking, is there's nowhere to hide. I mean, we have sampled unless there's lots of galaxies out there that we don't know about, even in the deepest observations that have ever been made, then the host AGN, which I think is quite unlikely, because we know most of the power is actually coming from the massive galaxies, that we have all the power that can be there. And the point is that we actually find that, as I said, that most of the black hole accretion occurs in the short AGN phase. The low rate phase has a rather small additional contribution, and our measurements generally fall well below earlier predictions, a variety of which are shown here. Okay, so many of these models, we feel convinced, will have to be revised downward substantially to reflect the new observational realities. And in fact, some people have started, we're actually collaborating with Marta Voluntari, and she's actually has one of her revised models shown there. Okay, now we hope to push this even harder in the near future. We're very excited, for example, about the James Webb Space Telescope, which should be fantastic in improving these types of analyses. I will first say that we actually have pushed even harder out to higher redshifts. Here are our results at redshifts of 4, 5, 6, 7, and 8. Okay? And so we've pushed this stacking approach all the way out as far as we can with the current samples of galaxies. And these are our, well, you can look here at the technical details of our measurements in terms of exposure times and count rates. We have mostly upper limits at the very high redshifts. The point, of course, is that when James Webb Space Telescope comes, and it will surely do excellent surveys in these same regions of sky, it will provide us with new large samples of galaxies reaching considerably higher redshifts, better redshift identifications, so we don't have to worry as much about photosync issues, for example, as well as better removal of low redshift interlopers. So the quality of the whole analysis will improve end to end. And so we aim to push these same types of stacking analyses with Chandra out to redshifts 10 to 15, we hope, with the large samples of galaxies that will ultimately come from the James Webb Space Telescope. But we could also envision taking the same stacking approach and applying it to other things, like 21 centimeter selected regions or things like that. Okay, so I will now just end with one other neat result in terms of what we're finding. This is just a neat thing that we stumbled into by accident, largely. This is work that was led by Franz Bauer, who again was here as a postdoc for a couple of years, I believe, after he worked with me. This is a serendipitous fast transient that we just stumbled across by accident in the Chandra Deep Field South. Here it is in the field. The Chandra X-ray Center put together this nice little movie showing the transient. It's here. And this was, again, a nice Chandra press release for us. And here is the light curve of this transient. Basically, Ben came to my office one day in 2014 as we were processing the new data, and he said, well, I see a new source in the field that we haven't ever seen there before. And it was actually, significantly bright, and it should have been a piece of cake. And here it is. Basically, this is the counts coming in versus time, and basically, we found a source that rose up to become quite bright, reaching a peak flux of about 5 × 10⁻12, that we had not detected at all back in 4 million seconds of precursor data obtained back here, okay, where it would have been easily detected. And it rose up with a very fast rise, and then followed up with a slower decay. That's the power law rate of the decay. It had a fairly hard X-ray spectrum. Here it is, sort of a typical effective power law photon index of gamma 1.4. And we had, just by chance, excellent optical follow-up. Someone by chance observed an optical, got a deep optical image of the Chandra Deep Field South 80 minutes after the transient occurred, even though we didn't know the transient occurred until a couple of days afterwards, just because this field, it's good to work in fields that people study a lot, because you get stuff for free. So we found, in fact, no optical transient, just 80 minutes after the event, ranging out till months after the event, where we actually went and got deep Hubble follow-up observations to try to see if we could see an optical transient. We found a clear counterpart in the Hubble imaging. It's that source there. It's an extended galaxy. It's a little tiny galaxy down at 27.5 magnitude. Okay, so it's very faint. Its photometric redshift is obviously very uncertain because it's down to 27.5. Our best estimate is at a redshift of about 2, but it could be anywhere in this broad range, honestly. But anywhere in that range, it's so faint, it has to be a little tiny dwarf galaxy to have this powerful transient. Here is a plot showing luminosity versus time for this source compared to typical swift gamma ray bursts, shown there. This transient we found at any reasonable redshift has a much lower X-ray luminosity than typical gamma ray bursts. Furthermore, its optical limits are also below those of typical gamma ray burst afterglows. Our best idea that we put forward in the paper is that this is an off-axis gamma ray burst, where the jet is pointing another way, and we just happen to catch a little bit of it. That's one possibility. We also admit to some other possibilities, that this could be a beam tidal disruption of a white dwarf, an intermediate mass black hole that could match the time scale, but the luminosity is sufficiently high that it would be super Eddington for a white dwarf, so you'd have to have a beam system if that was going to be the case. And Franz has done an excellent job actually mining through as much Chandra data as can be economically done, looking for more of these events, we find that this is the only clear example we find, but even with our current estimates, the event rate of these things appears plausibly to be comparable to those of gamma ray bursts. Obviously, it's uncertain, but there could be as many of these events going on as there are gamma ray bursts out in the universe. So this is a new, faint, fast transient class that will be exciting to explore with future missions, like the Chinese Einstein probe is very well designed for this, or other missions that some of us are thinking about. So I will end by just saying a few words about future prospects for X-ray surveys. First of all, Chandra and XMM-Newton are healthy and doing great. This is a little schematic here showing the state of health for all the Chandra subsystems, and essentially the colors are indicating that they're all working quite well. And so we can hope to have Chandra and XMM working until 2025 or beyond. So let's hope for another great 10 years of these X-ray surveys. And further, in addition to just doing these very targeted surveys, I will say that, of course, Chandra and XMM are continuously getting thousands of great observations all over the sky. And when things like LSST and PFS and Euclid and W first come along and do these extremely sensitive wide field surveys, they will make all of these wonderful archive data extremely powerful for massive, large analyses of X-ray source populations. I'm very excited personally about pushing the survey end harder in some directions. We had this meeting here, as Amanda mentioned, about LSST. LSST has decided to conduct very deep observations, deep drilling observations is what they're called, of a number of selected sky regions in XMM-LSS, in a wider region around the Chandra Deep Field South, and in another sky region called the ISS-1. We hope to get much better X-ray coverage of these regions. This would let us do all sorts of great stuff. We could study supermassive black hole growth across the full range of cosmic environments, ranging from voids out to massive clusters. And at a 50 kilosecond XMM depth, we would expect to detect about 12,000 AGNs in all these fields and about 760 X-ray groups of clusters. And this would have an incredible legacy value as DES and LSST deep drilling fields. And again, we've chosen these fields very carefully when we pick the deep drilling fields to have truly extraordinary multi-wavelength coverage, running from the radio through to the infrared, through to the optical, through to the spectroscopy. Very excited about VLT moons, for example, through to the UV. And so getting good X-ray coverage of these fields is extremely important so that we'll have this stuff when LSST begins operations. And we've actually been pushing on this with some success. Here, we've actually gotten now a 1.3 million second allocation on XMM-LSS. And here is our current observations of that. We have 1.1 million seconds of exposure. We've added to the exposure that was currently available in that field. This is being led by my postdoc, Chin-Ting Chen. And you can see here all the X-ray sources we have. Covered about 5.3 square degrees in total at a 45 kilosecond depth on average. And we have about 5,200 new X-ray sources, all shown here. We are now just working to get these matched to counterparts. We've had good success there. We have about a 90%, 97% good identification rate because of the excellent multi-wavelength data, which lets you immediately match this thing down on the counterparts, which we then will hopefully aim to target with spectroscopy. We also, sort of more generally, are excited about many other great multi-wavelength facilities. I've already mentioned, for example, the James Webb Space Telescope, but also, of course, as I said, the Large Synoptic Survey Telescope, we'll be doing deep drilling on the Deep Field South. ALMA continues to do great stuff there, VLT views, and of course, ultimately, the extremely large telescopes will be required to get spectra of some of the faintest X-ray sources we found. I'll also just mention that eROSITA is hopefully launching soon, and this will be a very powerful wide field X-ray survey facility that will be about 20 times more sensitive than the current all-sky survey, for example, which should detect about 3 million new AGNs. We also hope, ultimately, to get more Chandra Deep Field observations. One of the frustrations I have is that there's only 2 Chandra Deep Fields. I'd like there to be 100, okay? That's not going to be possible with Chandra. But something like Athena should be able to pound out things that are nearly Chandra Deep Field length and cover large solid angles to very great depths. And we have other ideas for missions that could do this as well. So that's a great possibility for the future. The NuStar folks also have great ideas for advancing hard X-ray surveys. NuStar was just an explorer of the hard X-ray regime. You can do a much more powerful version of NuStar quite economically with about 40 times its sensitivity and resolve the X-ray background up near its peak very effectively. And then finally, some of us are sort of, I would say, dreaming perhaps about missions that go far beyond Chandra. We're in currently NASA is studying a mission called LYNX. Here are a group of us who are thinking about this, which would go far beyond Chandra's sensitivities in terms of direct detection. Would have Chandra-like imaging, but with 30 times its collecting area, which you can actually do fairly economically with advancements in mirrors. And with a mission like LYNX, you could aim to go out in a redshift and directly detect the seeds of these supermassive black holes. You could reach down to sort of 30,000 solar masses to find even the obscured systems. And that would let you go and directly discriminate, for example, low mass population 3 remnants from direct collapsed black holes. So anyway, those are some of the things I've been excited about and working on for the past couple decades. So thank you very much.